So we're going to define two very important ideas in the next one. Faraday's law, which is to do with the amount of EMF which is generated in a coil or in a wire. And number two, which is Lenz's law. So those two big ideas you need to have a clear picture of by the end of this video. So first, we are going to define a quantity called magnetic flux. Magnetic flux has an official definition, which I'll go into in a minute, and a really common sense picture, which I'm going to draw for you right now. Magnetic flux generally is simply the number of field lines that you have cutting a certain area or inside a certain area. So here you could say, oh, the magnetic flux is 1, 2, 3, 4, 5, 6, 7. Okay, it's a measure of how many of these field lines you have in a given space. The official definition, however, is a little bit more complicated because it's in terms of the field strength here. Now, I would, if it was my physics universe, I would have done it in a different way. I would have spoken about magnetic flux first and then defined field strength. But physics doesn't work that way sometimes. Let's have a look at field strength. Field strength is the number of field lines, flux, phi, okay, per unit area. That's how you know if a field strength is very strong or not, if the lines are very close together. So, it should make sense to you now why the actual definition of magnetic flux is actually equal to the area times the component of the magnetic flux density, B, perpendicular to that area. So, phi, the magnetic flux, unofficially the amount of field lines in a given area, is equal to the field strength, the number of flux lines density, times the area in question. Now let's have a look at this idea of perpendicular to the area, because I haven't mentioned that yet. Why do we need that? In order to do correct calculations of flux, how many lines in a given area, our area in consideration must be perpendicular to the field line direction. As you can see in this example, that is not the case. You can see here that the field lines are at an angle, theta, to the perpendicular. So we want to know how much of this field strength is perpendicular to the area in question, which is this area, the area of the coil. So B is the hypotenuse of a triangle. B is the actual maximum amount, so we need to find what component of B is acting perpendicular along here. So this is a bit of an upside down right angle triangle, and you should be able to see that the component of B in this direction is B cosine theta. Now, in terms of actual questions, you just have to take that into consideration. Make sure that your area in question is at 90 degrees to the field strength, and if not, you have to try and figure out where the angle goes. In any case, our final equation is that magnetic flux phi is equal to BA cosine theta, where A is the area and B is the magnetic field strength. Now, in addition to this, you do actually have a magnification effect. So if you have a single wire moving through field lines, then what's important is the number of field lines that you move through. Okay, so in the case of a single wire, we would just talk about flux area, okay? But we need to think about something called flux linkage. This is what happens when you move away from using a single wire and you turn towards a practical system which has more than one conducting coil. So what do we do in that? We're getting a magnification effect. The number of lines that you are considering is multiplied by the number of wires that you have in your coil. So whatever effect that these field lines is going to cause in your wire, if it's going to generate an EMF, there will be a magnification depending on the number of coils. So we call that a flux linkage. And flux linkage is simply the flux times the number of coils. And our magnetic flux linkage, which is the magnetic flux into consideration, considering the number of coils, okay, is N times phi, which would be N times B A cosine the angle. Okay, so what are the units of magnetic flux? The units are Weber. Okay, so magnetic flux and magnetic flux linkage both have units of the Weber, and by definition, 1 Weber is equal to 1 Tesla meter squared. And by that, of course, I mean 1 Tesla times meter squared. All right, okay, so it should make sense. Tesla being the unit of magnetic field strength, and meter squared is the unit of area. Okay, so there you go. Okay, so let's try this simple question. What is the magnetic flux in a square coil of wire size 6.2 centimeters when it's placed at 45 degrees to a magnetic field strength of 4.3? Heavens. Well, have a go at that one. So here is a diagram sort of trying to depict what's going on. You have a rectangular coil. So this rectangular coil has an area here. And what you have to work out is how many of these field lines are going to be in this space here. Okay, so the area is really important, and the area would be 6.2 times 2, and of course it's centimeters, so it's times 10 to the minus 2. Okay, centimeters, 10 into meters. So that would give us our area. Now the problem, of course, is that the field lines are not perpendicular. Okay, so we need to add that cosine times cosine 45 degrees, and then times the magnetic field strength, which is 4.3 times 10 to the minus 4. And that will give you your flux, which is the amount of lines in this little area here. Okay? Okay, which we can see the answer here is 1.2 times 10 to the minus 6, and I hope you got that right. Now what would happen if only half the coil was in the magnetic field? Well, if only half the coil was in the magnetic field, then your area would be halved, and so you'd have a smaller. And if we look at the formula, it's phi equals BA cosine blah. So if that is dropped by half, then phi is dropped by half, and you only get half the effect. These questions are almost exactly the same. Question 12 is about flux linkage. Okay, so it's no longer just BA cosine the angle, it's NBA cosine the angle. It's the flux linkage, because we have 480 turns. And apart from that, these questions should be very straightforward. If you get stuck on question 13, there'll be a little bit of advice later on. So here are the answers, and if you had a bit of trouble with question 13, there's just a few things to consider. Firstly, we're considering the change in flux. So you need to work out the flux at the beginning when the axis was originally parallel. Okay, so if this is your coil, the axis is that line in the center, and if it's parallel to the field lines, then what you have is the maximum situation. So you've got this NBA, and cosine is equal to 1, because the angle theta is equal to 0. So you work this out, and that will give you your maximum linkage. Now, when you move the coil that coil an angle of 25, then you need to work out your new flux linkage, BA cosine 25. Okay, and your actual answer would be this minus this, which will give you your answer, 4.5 times 10 to the minus 4. Okay, so now we understand what this idea of flux is, and we've had a bit of a play with the relationship. We can now look at how it's relevant to generating electricity. Now, electricity is generated by moving a wire near a magnet, or by moving a magnet near a wire. So there's a couple of important aspects to this. The first thing is that you are moving something. The second thing is that you're moving a conductor, right, near some kind of magnet. There has to be a magnetic field. Now, how does this change if I do this? I move a magnet near a wire. Well, the important thing is that they are moving with respect to each other. So you can get current flowing if you move a magnet in, or if you move a coil in that way. Okay, as long as there is a relative moving. Now, what has this got to do with flux? Well, when you're moving either a conductor, actually make it bigger, if you're moving a conductor inside a magnetic field or the other way around, what you're doing is you are cutting the lines of flux. So in this, for example, you are moving the wire in an upwards direction, and the wire is gently cutting an area of flux lines. So you can always visualize the wire literally breaking up these green lines, cutting the lines of flux. And it doesn't really matter how that happens. What's important is that the lines are cut, because it's the cutting of the lines that creates the EMF. Now, there are 3 ways that this effect can be produced. The first one is that the circuit, the conductor, is moved through a magnetic field that is standing still, like here, in this case. The second way of doing it is to move the magnetic field, right, and keep the conductor still. So in this case, we have a solenoid, a coil, which is standing still, and what you do is you move the magnet into it. Now, because the magnet is moving, the position of these field lines changes, and the wire ends up cutting the lines. Now, the third way of doing this, and this is where it gets really exciting, is to not move anything at all, but to use a current, let's show you here, you're going to use a current to make a magnetic field which changes, right? So if your current varies, say for example you close the switch, then what you're going to suddenly get is a surge in current. Now that surge in current will cause a magnetic field to suddenly appear, and that sudden field appearance will create a pattern of changing field lines. And those changing field lines, if there is a wire exposed to it, would induce a current in the wire. So what you would get here is if you switch the power on here, you would suddenly get a little switching current here. It would just switch, it would tweak a little bit. Now this is super important, and this is pretty much where it's all at. If you vary this current, let's say you send a current which is changing and it's going up and down like that, then you can get some really exciting stuff, because then what you'll produce is a magnetic field in this wire which is constantly changing in exactly the same way as this one is. And because it's constantly changing, the field of lines are constant, the field of flux, the lines of flux are constantly changing, and so therefore this wire here is being exposed to constantly changing lines of flux, which would cause a current to be generated here. Okay, so let's just sum that up. There are three ways. The first way is for a wire, a circuit, to be moved through a stationary magnetic field. 2, the magnetic field to be moved into a circuit. Or number 3, a changing current in one circuit produces a changing magnetic field which spreads out and passes through another circuit, causing a current to be produced in the second circuit. Now it's probably a good time now to stop and have a look at some of the other videos to show this, as they're a little bit better at demonstrating the visual aspects of this. So stop and have a look on the site. Okay, so let's get back to induction, the producing of a current. Now, electromagnetic induction, or more specifically, an EMF, is induced in a conducting wire when the magnetic flux linkage changes with respect to time. This is what makes electricity flow, a current, or induces a current to flow through a conductor. Okay, the fact that you are cutting lines of flux and the speed at which you do it is also very important. Okay, so let's go back and define flux linkage. If flux linkage is N times phi, okay, how do we then define the rate at which this EMF is induced? It's called Faraday's law, and this is really, really important. You have to learn this off by heart because it gets asked every year. Okay, I'm exaggerating, but it gets asked a lot. The Faraday's law states that the magnitude of the EMF produced is equal to the rate of change of magnetic flux linkage. So in non-physics terms, what this means is that you get more EMF if you cut more lines in less time. The quicker you cut field lines, the more EMF you get. Okay, so in the previous examples, the faster you move your magnet, the faster you move your coil, for example, or the quicker your current changes, the greater the EMF produced. So there are two ways of expressing this. Number one is N phi over delta N phi, over delta T. And another way of expressing it is to expand that to include the relationship we were using before, delta NBA cosine theta over delta T. Now don't worry about the minus. Some of you guys get really excited about minuses. We will come to that. Okay, so this is Faraday's law, the rate of change of magnetic flux linkage. Remember, rate means per unit time. Here's an easy peasy question just to get you warmed up. You have a conducting rod of length 1.2 meters moving perpendicular at a speed of 6.2 meters per second through a continuous magnetic field of magnetic field strength 2 times 10 to the minus 3 Tesla. What is your magnitude of EMF? So how do we do this question? Remember, our relationship is delta NBA over delta T. I'm not worried about the cosine because there's no angle here. So what exactly is changing here? Well, it's moving, so we're considering the change in area that we're cutting, okay? So this little bar is moving this way at a speed of 6.2. What is the area? Well, it's drawing out a distance here of 6.2 meters in every second, in 1 second, right? And what is that area equal to? Well, the length of it is 1.2 meters, so it will be 1.2 times 6.2, which equals 7.4 meters squared in 1 second, right? So that gives us your change in area, and now we just multiply that by the field strength. There's no n, so we don't have to worry about the linkage aspects. So we just multiply it by 2 times 10 to the minus 3. Okay, and you should end up with a value of 15 millivolts. So hopefully that makes a little bit of sense. Okay, so these are some very simple questions to try. A coil of area 4.7 centimeters squared and 480 turns is in a magnetic field strength of 3.9 times 10 to the minus 2 Tesla. What is the flux? Okay, so that should be very straightforward. You're just working out phi. Okay, and then part B, what is the average induced EMF when the coil is moved to a place where the perpendicular magnetic strength is 9.3 times 10 to the minus 3 in a time of 0.22. Okay, so what we have there is a change in, this time, in field strength. So if our relationship is as follows, change in flux over change in time, okay, we work out our new value. So your answer to A is what you had at the beginning. Your average induced when the coil is moved to a place where the magnetic field strength is 9.3 times 10 to the minus 3. So from here you need to work out a new value of phi. So you then work out the change. What is the difference between your value of phi here and now your value there? And then you do minus, okay, over that time. Okay, you should have these two values. So basically, either your value of field strength changes or your value of area changes. And that would give you a quantity for change in flux. Okay, so you just need to figure out in the question, is it asking me for the change in field strength or the change in area?